Okay. Think the okay. Okay. So last week I think we finished most of the torsion sections. So for today's class, I would like to move to the new chapter. In your textbooks, if you're using the same textbook as mine, this is the new textbook. The new textbook. My chapter for the next one, I will skip one chapter. So the chapter will be the equilibrium of the beams. Okay, so we are going to move forward to chapter 6. And for chapter 4, some exercise and practice we are going to see in the Friday class. Okay? More in Friday class, and later also I'll put in the Moodle. And also I'll put in the Moodle, I'm still designing the your additional works for your midterm. So hopefully, maybe tomorrow. I already have designed, but not yet finished. So hopefully tomorrow I can put into Moodle. And then, since we finished chapter 4, and we are going to have more practice in chapter 4, you need to be prepared when we have maybe a quiz later on chapter 4. So the quiz will be on chapter 4, torsion. So torsion, twisted angle, okay, finding the torsion or finding the twisted angle. That's I think the case mostly. That will be the main idea on torsions. Now we are moving to the equilibrium of beams. So let me start with the new chapter here. So there are some picture here. Let me just make it small a little bit. So let me make the title equilibrium of beams. So this is chapter 6 in the textbook. So torsion, chapter 4, the equilibrium of beams, chapter 6. So chapter 5, I will skip for now, but if we have time, we will go back to chapter 5, because chapter 5 is about the transformation of stress strain. Okay, so that will be about how we are going to see mechanically the behavior, the difference for some materials. Okay, so we can see from its stress strain behavior. Okay, and the way we distinguish between those materials is based on what we call, the method is called using the Mohr circle. The Mohr circle, I think that will be very important, but I think I will give that after, maybe at the near the end of semester. Okay, I will give the definition of what is the Mohr circle. But for now, let's go for the beams. Okay. So the first thing that I want to mention about this sections is there will be some. If you remember that we are going to have some support, okay, for beams. So this is I think example. So first is they are distributed load, and you see that they are supported here in A and in B. This is we call this simply supported beam with distributed load. So we are going to see that first they are having roller support, and this is just a fixed support. Okay, so you're going to see that the reactions, because it has roller, it can move freely on this axis, right? So we are just going to see one reaction force, right? For this one, we have y-axis and x-axis that has the reactions. So yeah, based on the support, we can distinguish how the reaction force will be. And then we are going to see cantilever. Okay, cantilever. Now having some couples here for a moment, and then a concentrated force at B, And then here, because it's stick to the wall, we can have all the three internal forces, okay? And then we can also see the continuous beam and so on and so forth. You can see I think this is the same instruction as we did before, but I will emphasize that we are going to see more on the bending moment and the transverse shear. Basically, that is on, if we see this internal force, we are going to see more on this M, okay, and then this one here, the shear, okay. That one we are going to observe in more details within this sections. Okay. Okay, let me give you some. Before we go to this part here, let me go to just giving you some context. Okay. So suppose that you are having a shuffle. So perhaps if you imagine like a farmer doing some labor, and then you pick some dirt or maybe some grounds from the farms, okay, and then let's say this is your hand. Suppose that can be seen as hands, okay? Although it's not very clear, okay, let's pretend that this is your hands. So imagine that this is a shuffle that's supported by hands, right? So you have a weight here, right, which is maybe some certain value. And then we could take this and then look at the forces that is going to be defined. Okay, let's say that's our, so this is having some W there. And let's say we are going to have 3 different points based on the support. Okay, so let's say this is going to be point A, point B. This is A, this is B, and this is C. And let's say we are going to have some distance. Let's say distance through here. Okay, so that's the concentrated weight over there. So this is some length, and then we are going to have some length defined between our hands. Okay, so this will be, let's say, some small a, just to denote that we can change this distance by our hands, right? Okay, so another point that we are going to write inside this diagram is the reactions, right? The reactions, well, suppose that this is as a simple support. I think we can just imagine that this is going to be having reaction force at A and at B, right? So both sides having some supports. Let's say this is supports going to be like that. And let's name the force as RA and RB. And then based on what we have here, we can rewrite that RB is RA plus W. So this is, we call the free body diagram for the macro level, or the entire subject, right? Okay, and then as we usually did, is we are going to take some sections. So let's cut this into pieces. So let's try to cut, let's say from A to B. So let's cut open. So this is still RA, and this is RB, which is RA plus W. And then we are going to have some shear between this cut. Okay. So this is A, this is B. And then let's imagine that inside the shuffle, the tube, we have some distance that we are going to have, like maybe this is a hollow. So we have some diameter, or maybe let me just write this as a distance, some B, okay? And then we can also take this up until some C, nearby C. And then inside this force, or the internal force, we are going also to see the normal, right? Well, some may be like that, or maybe in another, maybe let me write clearly, so we can have, or maybe let me make a little bit gap, so we can have that way or that way. So this will be a tension for the side, okay? And this will be a compression for the sides, right? And the shear force here is typically equal to the weight, okay, to the weight of this shuffle. And then this is weight. And then this is distance A. And then up through here, from this B actually, let's say this is the B is here because it's cutting through there, that point, up until W. And let's say this will be the L minus A, okay? So this is, we say that this is a free body diagram showing the resultants of all stress at the cross sections, right? So we can write down some formulations that we usually take for the statics. So equilibrium equals 0 for the forces and the moment. And then based on what we have here, let me write the final results. So RA is W L over A minus 1. So we take the moment, okay, and then we take the force, and then take the equilibrium, and RB would be W over A. And then let's take some sort of experiment with the hands, okay, with your hands here. So first is let maybe this is hand 1, this is hand 2, okay. So first experiment 1. So moving to, okay, from B toward C, okay. So this is saying that A is getting L, yeah. It's approaching L, so we are going to move our hands closer to C, okay. And then we are going to see from this formulations, we are going to see that if we get this closer to L, then the RA is somewhat going to be 0, right? Somewhat going to be 0. So RA is going to be closer to 0. Let me write with arrows to denote that we are going to see this approach, okay, like using in limit, okay? And then RB is going to be equaling to the weight itself, right? And I think that is really intuitive, right? So if we move our hands towards near the weight, our hands becomes the one that nearby the weight will be very, very heavy, right? Okay. And our hand in the one that left behind is getting lighter, right? So it's not as heavy as it is. And then this is also, we can take the RBA equal WL. This is a constant. So no force at A, it seems, right? Let me move this first, it's going to be here. And the hand at B will be directly under the load of the weight in this shuffle, right? And then the next one, experiment 2, let A approaching 0, which means that this hand is getting closer each other, okay? The two hands become closer, okay? So we are going to see that RA, based on this assumption, will become or going to approach infinity, right? And RB also getting infinity. And remember that this is always a constant. Okay. So the RA and RB will be larger and larger. Larger, and I will write here, much larger than the weight itself. But the moment, the RBA, still the same. Okay, and now from these two experiments, we can see how much changes for the forces if we change the distance, right? If we change the distance, the reaction force also change, right? And now let's focus on this. So this graph here that I already cut. Okay. So we have here, we cut the this shuffle, the handles at the B point, okay, the point B. So we say we have a transverse shear force, okay, that is equal to W, that is required to satisfy the equilibrium, okay. So this one here, this is required to satisfy the equilibrium. And the tension and compression within this shuffle, because there is no external loads on the horizontal parts, so we can say either way they are going to be the same. Okay, either they get tension or compression, they should be the same same value. Okay. So the cross section itself, they need to have some couple, okay, to be applied. That let me write here. So I think maybe blue. So let me write here. So to support, okay, the cross section, must supply couple of the magnitude of the bending, okay, WL minus A. This is what we call the bending moment. So to form this couple, there must be equal and opposite horizontal force that makes the compression equal to tension that acts on the cross section. With a moment, the moment arm, such B that is really small compared to the length of the shuffle itself. Okay, so you could imagine that the distance, maybe the distance between the handle, okay, maybe the diameter of if this tubular, okay, and then we get that such that C or T is equal with this value. So within these cross sections, we need to have the both compressive and tensile or tension stresses with the magnitude of the resultant compressive force and resultant tensile force much greater than the external load W. Okay? Okay, I hope you can get the idea. So what does it mean is we need to have the resultant force. Maybe if we use our hands, then our hands need to apply forces that is equaling or greater than this magnitude. Okay, this magnitude value. Okay. So you can imagine if you want to design like this simple for farmers like a shovel, how large the handle will be, okay, the distance. You could imagine like if the handle too small and maybe the farmer's not really put the distance within hand, so it's not efficient, the shovel can broke, right? Which means that it's broke on its bending side. Okay? So that's the bending moment that makes the shovel broke. Okay? Okay, so as a conclusions, this picture here telling us that we see that from here that a transverse shear force that is Vc and bending moment that MC must be acted at C to maintain equilibrium. Both force and moment. Okay. So this is just an introduction. These introductions. What is actually the shear force and the bending moment? Because later on, I think after a few sections, we are going to see that we can apply this kind of, like from this picture of the loads, distributed loads, we can also observe through or analyze through the shear bending graphics. So we can make some graphics through the loads here, how it looks like, and how we can find also the bending moment from one schematic diagrams. Okay. Okay. Now the next thing, okay. So we know that there is something here, so we need to know how to use this bending moment and the transverse shear force in more practical way. Right? Okay, so first is define the shear force and the moment through the integral definitions. So based on a small partition in every element here, and so we take this as a shear force. Okay. or shear stress here, and this is the normal stress, and this is how it looks like in general view. This is the resultant for the shear force. This is the moment. From this one, based on these stresses, we can apply to write the formulation for both M and V. So V is going to be integrations of this tau, and then dA for every dA here, and M is going to be some multiplication from this normal stress with some y. Can be go here, okay? Depends on how we see the elements. If the elements here, then this is our y, then this will be the moment, okay? Okay. So we call that this is the stress resultance. And the practical way to see is we need to make sure that we can apply the sign conventions. Okay? So this will be for the sign conventions. So to help you to observe. So sign convention, so positive shear V, it will act in y direction, in negative y direction, sorry, on positive x phase. And then positive bending moment. M makes a positive y phase on the beam concave. Means this is positive moment, making this concave. And it's the positive shear, and then as a conclusions, positive will be making these two sides of internal forces you see. So what this actually means, and for what does it really affect us, is basically we are going to take this description through the later on the shear moment diagrams that can visually give some abstractions or descriptions on how the conditions will be. If you are having some object or some system that has some mechanically loads, we can input those, and based on our analysis, we can see where at what distance that the system is going to have like the maximum bending moment or the maximum shear force. Okay? The maximum shear force. Okay? So before we go to the shear and moment diagrams, that will be, I think, very at the end of the sections in chapter 6. Before we're doing that, let's see on how we take the equilibrium of beams using the finite free body diagrams. Okay. And I will just give you some examples on how we analyze. Okay. Okay, so this is the cantilever beam AD. This is the figure 1. So let me make this a little bit smaller. Okay. It's subjected to a concentrated force at C, 5 kilonewton, and couple, that is 4 kilonewton meter at D. So it's cantilever. So cantilever means that one side will be in a fix. So probably imagine like a wall. Okay. So the couple is at D. So determine the shear at B, VB, and bending moment, MB, at a section 2 meters to the right of support A. So this B is 2 meters from A. And all the length given by this picture. So 3 meters, 3 meters. So it's on the middle of the beams, the loads. So first we can take the free body diagrams. Okay, let's say we can cut at B. Okay, we can cut at B. So let's say we are going to slice this point. And since we are having more information on the right side, so let's just focus and see the free body diagrams on this side. Okay. So we have the 5 kilonewton here, we have the moment 4 kilonewton meter, and we have some length. Okay. And we know that the length 3 meter, 2 meter, this will be 1 meter. Okay. So we can take that and first, as usual, calculate the equilibrium. So it's not really that different from what we have done before. So first steps, always take the free body diagram. So let's write here. This is going to be that 4 kilonewton meter. This is D, this is B, C. Five kilonewton, and this will be VB, and then having MB over there, right? And then we have 1 meter over here. And this is 3 meter, right? So this is our FBD. So let's just take this FBD. And then write the equilibrium. So we know that VB plus 5 kilonewton is equal 0. So from this part, we know that this VB is negative 5 kilonewton. And then say take the sigma moment at B that is equal to 0. So let's take this as a positive, okay, or forget this is positive, just to make sure. Otherwise, actually, as long as you consistent, I think no worries about the signs. Okay, but to make sure observations are clear, you can always do these things at the first equilibrium calculations. So now we take MB, right? That's positive, and then the 5 kilonewton and 1 meter, it's going to be counterclockwise, which negative 5. And then plus 4 kilonewton. I think there are no other relations from here. So this is equal to 0. So MB is negative 1, going to the other side is 1 kilonewton meter. So the actual graphs for our solutions. So this is just a simple questions. So our components, the phi should be going down. It's too long from that point. Let's write a little bit closer there. 5 kilonewtons, so B, sorry, C, and D is 4 kilonewtons. And then to check, we can check our solutions. So in our course, you can always check at the end of your, especially for equilibriums, you can check the numbers again, put back into the equations, and make sure they are going to be 0. Okay. So check this. So let's say we are going to take the sigma moment at C, let's say at C, and it's going to be 0. Okay. Sigma moment at C is going to be, it has 1 kilonewton meter, right? It's positive. Let me write here, it's positive. Okay, let me finish this first, just writing this. And this is equal to 0. So check the result on another perspective. Okay, so let's continue. So this is just like a pretty simple conditions that we can observe the cantilever beams. Okay. Another, let me check. Okay, let's skip this. Another sections. This is more like about the still a little bit introductions. Okay, for especially here is for the sign conventions for the external loads. Sign. So this will be a positive signs, right? Going to the y directions. And for the moment, for the counterclockwise, this is considered as a positive. This is considered as a positive external couple. So this is a positive external loads, or positive distributed loads. Okay, so as we analyze, if we take the equilibrium, okay, so equaling this to be 0, and if we try to break down what will happen, or maybe before that, let me write notes first. So consider a portion of the beam where there are no concentrated loads or external loads. So we are going to see observation on infinitely small or infinite small infinitesimal free body diagram. So let's take the delta x here as our segment. So taking that from x to this x plus delta x, and we redraw this, and then it's become this one here. So we are going to see another sections. So first this is the general free body diagram for the small sections of the beams. So all the external loads become distributed loads, the small distributed loads, the small segments. And the moment also we consider this delta here, okay? So now, taking this into our considerations, taking the equilibrium, so we are going to have Vx plus, we are having P multiply the delta x and then plus, let me write first and then explain later. This is called O. Let me explain that later. So O is means of the order of, and suppose that the delta P is equaling this delta x, and then we can rewrite V x plus delta x minus Vx is equal P x plus O delta x. Okay, and then taking, so O doesn't really matter for now, okay? So just bear in mind, taking the limit as delta x is getting 0, we get that this is going to be dv dx. Okay, so this is the definitions for the derivative through limits, and then this is equal to px. And note that limit of O term is becoming 0. Okay, same way, we take the sigma moment at C, that is going to be equal to 0. And from this sections here, we are going to see that this is going to be mx minus m x plus delta x, and we compute the other components using the p and v, so plus px and delta x squared over 2, and then plus O delta p delta x squared plus phi x delta x equals 0. So as limit as the delta x getting 0, okay. So we take the terms, simplify, and this is going to be dm dx is going to be equal to vx. Okay. Okay. So from the infinite small, let's say this is our conclusions. Okay. So what this is going to be as a consequences. Okay. Here's saying that this is going to be like a shear jump and a moment jump. And what is that? So first, if we take this two picture on the right side, the V and the M, if we take the equilibrium again, if we take the equilibrium, let's say equilibrium for the shear, okay, for the y-axis, for the force, for the second picture, we see that this is going to be VA, VA, and then minus, okay, minus VA plus delta VA. So VA minus means that it's going to be after taking the limit, okay? So this is going to be plus P0 equals 0. So delta VA is equal P0. So whenever there is external force, let's say in our case here is the P0, okay, or couple, like in the in the third picture, it's the M0. There is there will be some change. There will be some small change, okay, small change, or to be precise, step change, like step in the stair, okay. In shear or moment. Okay, this negative, if you're wondering, negative means left side, okay, internal force. Internal shear force to the left of X. Or XA, let's say XA. So P0, as a conclusion, P0 will cause a step change. Step change. What is the step change? This is the delta. Okay, step change, the delta VA in shear. Also in the sigma moment, let me write. Let me write a little bit over here. So in the sigma moment, say B, so MB negative, the left side of the XB. So because of the M0, that we will have the small step change. So again, this is a step change. Okay, perhaps it's still a little bit abstract in what it is, and perhaps there's, I think, maybe you're still wondering what is this about and why there are so many delta and then X plus delta, blah, blah, blah. I think this will be very clear if we are going to have the shear moment diagram, okay, and that will be more, I think, more practical. So this is just an introduction on the using the limit approach. Okay, we are taking the small element, and then by looking at that, we see that there are, if we take this is small element like this, every time we have an external force, like the P and M, if we analyze through the distance, so with the distance here, we're going to see that if we imagine the shear force, maybe it starts from here. If we have the external force of y, it will be a jet. Okay. If we make the distance and shear as a diagram. Okay. And similarly, if we take the moment, at some point, perhaps it's going to be having a parabolic curve from the distance and the moment, and perhaps there will be some sort of change here, and then perhaps it's going there. Okay. So that small change, or this we call it step change, is because we apply the external force. So that's the implication. So I think we can just move on and looking at the shear moment diagrams. But before that, let me just make sure that so if this is our analysis, okay. So let's say this is our distributions. So this is getting like, let's say it's random, okay? Random distribution like that. We call the distribution as Px, and we are going to have V1, V2 for the shear force, and then M1 and M2. And of course, we have all the distance for each component. So this is for component 1, and this is for 2. And let's say the x is on between this x1 and x2. So based on what we have here, or maybe it's not fully aligned. So when we have here, we can take this y-axis either as a v or as m. Okay. And then we are going to see how they behave when we apply into our x. Okay. So of course, if we look on what we have here, the load has a distribution. Okay. And based on what we have, we can take the V2 minus V1. I will directly just write the formula. It's equal to integrations from x1 to x2 of Px dx. Okay. Okay, of course, that is by definition, right? We take the V2 minus V1, and then we have all the integrations from this x1 to x2 of this dx. Okay. And let's say the dx have the dx, and we have the area under the curve for the force, right? The force is acting as an external force like the previous one. And then we take the moment, and actually the moment is the integrations of v. Okay. So let me write directly here that m2 minus m1 is okay. So this is kind of having some relation between v and m based on what we define with this integration. So that means if we have v and distance, let's say it's linear, then the moment will be a parabolic, okay? Based on the integrations relation. Or if this is, let's say the v is a constant, then the moment will be linear. And according to what the v behave, either they are going to be maybe in the negative or maybe positive. The integration will take that as a node. So you need to take some review on your calculus. Okay, and what we will have if the slope is positive, if the slope is negative, what will be if we integrate? Okay, so of course if you have line, it will be parabolic. If you have parabolic, then maybe if you integrate another parabolic, it will be cube, right? Okay, so that is my tips. So you can take a look from those relations. Okay. So we can take this actually right in the using fundamental theorem of calculus. Let's say we take this in terms of from x1 to x. X is our variable, so we need to describe in another variable inside. Let's say t. Okay, let's say t. T is just our dummy variable, cannot really have a meaning. Okay, let's apply in our example. Let's write example on below here. So let's suppose that we have a beam. Let's say this is A, this is B, this is C. And let's have the distributed load over here. And also take a triangle over there. Okay, so remember, integral is about area under the curve. So basically, if you are given an area that has a specific geometry, what you need to do is just finding those areas. Okay, so you just multiply the area. Okay. So this is 1.8 meter, and let's say this is another 1.8 meter. Oh, it's supposed to be in the middle, but I think let's make it better. Maybe make it more proportional. And then what else? Oh, we have the external loads. Oh, suppose that we already have given the information on the external loads and the internal supports. The reaction force is this 900 Newton. This is 630 Newton, and the distributed load is 600 Newton over meter. All right. Oh, it's not 900. 990. Sorry, 990. Okay. What else? Okay, I think. And this part here, the triangle need to be go to the go to be the last one here. Okay. 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 Oh, it's supposed to be already here. I need to. Yeah, this is from another example. So this 990 and 630 is actually unknown yet. So you can find out first, and you get 990 and 630. So you're using the equilibrium to find that. Okay, using the 600 Newton per meter for the distributed loads. So the original questions is without this. So first you need to find this first, and I'll give you right away. And then the next question is to get the diagram. So plot shear moment diagram. And then determine the location of maximum bending moment. And I think if the graph or the system is quite simple, you can predict where the maximum bending will be. Can you predict where is it? Where's the maximum bending moment? Okay, let's just go through the graph, okay? So, the first is taking this into graph. First is taking the v and x, right? Distance. So v is in Newton and x in meter. Let me check first whether we have another informations. Okay, I think we can also write some notes about this informations as the free one. If we take this integration here, so if we take the free one, is basically 990 minus 600x. So we take variable x. This is for x between 0 and 1.8 meter. And then V2 is 630 plus let me just write the result. This is Newton in Newton and 1.8 and simply we are taking integrations from the V1 and V2. This is going to be divided by 2, it's 300 x squared Newton meter from 0 to the 1.8 meter, and M2 630 3.6 minus x and now it's going to be Q, or it's wrong here. It's supposed to. that way. So this will be Newton meter. Okay. So V1, we can take x equals 0 to make sure that V1 is 990 from, and also this is taking from the picture. We can make sure maybe this is our starting point. Okay. And then we are going to see that what we have here, suppose that this is going to be 1.8, but we need to check whether this 1.8 is getting 0. So we need to check the x. So taking V1 equals 0. So let's taking V1 equals 0. So where's V1 equals 0? So this is going to be equal 600x. So x is 990 divided by 600. So x is 1.65. So it's not perfectly in line with the 1.8. So we need to shift a little bit to the left. Okay, shift a little bit to the left, probably around here. Okay, so this one here is going to be linearly going down like that. Okay, the linear coming from this linear equation. Okay, and then what will happen is, suppose that we are going to have the 630 Newton. So maybe around here, let's say 630. So after we move to this 1.65, then we are going to use the second formulations. Okay. So how we get this expression is through the equilibrium for all the forces and moment. Okay, but I think we can review this later. Okay, I think in next sections. And then we have this parabolic through. And then this is going to be 3.6. So at 3.6, if we calculate through the V2 here, this is perfectly making 0. Okay. So we take that as a parabola. Okay. Okay, let me put this a little bit down here. Okay, so I will put this V and then copy and make it here. Okay, and make it a little bit smaller. Okay, now is we are taking, let's expand the V and then taking this as M. And this is X. Now the moment, since we already have the equations here, we can take the moment, but actually you can apply your knowledge in calculus. Okay, so if we have this, this is your shear diagram. So as it is crossing this 1.65, if V is the derivative of M, okay, so this part here is positive, right? It's positive, okay? So if you want to make a graph that has a positive slope, is it going to be like this or this? This, right? So you can actually estimate how the graph will look like. So it goes down here and here, right? But it's still in positive, right? This is negative. So in positive, you get here, and then change the slope and going down. So here, because it's perfectly straight line linear equation, it's supposed to be a square parabola, okay? But after this part, it's already parabola. Now it's going to be cube, so it's a little bit slightly changed, but still it's curvy. Okay? So you can just write or draw like that and like that, and you need to make sure that this is different from this part. Okay, so this is square, this is cubic, and where's the maximum? At 1.65. Okay, so nearby the 1.8. So we get maybe going that way, and then this is a little bit having a slope like that. Okay, I think it's still the same. Maybe may change this into a little bit. Okay. So this is the M max. What is the M max? We can take that into our equation that we have and plug into our this point. Okay. So when X is 1.65, this is M max, right? So take the M 990 or let's taking the M1. M1 is, what is M1? Okay. So taking the M max is the M1 multiply with the X M. So let me write here is 1.8. This is XM is 1.65. This is 3.6. So if we put M1 here, I didn't bring my calculator. So put here 0, 1, 6. Let me just checking my numbers. Multiply with 300 minus 816.75. So 990. Okay, so I think we can just write using the M1. So M is 990 this will be M max equal to 816.75. Okay. So this is the bending moment max, and this is the diagram. Okay. And actually, to estimate the diagram, before you set up this formula, you can figure it out through the through this distribution. So you can see that from here and up to here, you will see some change in shear, right? You can predict how it looks like, and then to get into the moment, take the integrations from that graph. Take the integrations. Okay. But for the exact value, then we need to go back to our equations. Okay. So I think next, let's describe that formula from the examples. Okay, I think we don't have much time, so I will review again. I will get this formula. Okay. Okay. Maybe the last part is here. Last part is this. Just some notes, okay, that helps you through the picture and figure. First is if the shear diagram. So this is the load. This is the load, the shear, and the moment. Okay. Now let's see if we take some external force. Okay. So first is this is what we had before. Okay, so if we take this is going to be integrate through that. So let's say we have this. Okay? We have the external force, external the P0. We are going to have jump. Okay? We are going to have jump. So the P1, and then we have jump, and then because it's constant, no distribution, right? No distribution, so it's constant. So we have this kind of gaps that we say that this is going to have a jump. Okay? And then because this is a constant, take integrations, we take linear and then linear. Okay? And then we have the distributions. Okay? So we have V2 minus V1, and then this is the area. This area under the curve. So how to take the area under the curve is basically you take the geometry. Okay, the geometry. You can check the area here, and then this one in the height. So the area triangle, and then area of the rectangle. Okay, you can take that as your area for the integral. Okay, and then take the integration that becomes another slope. Okay. This one here we can also see if we have a slope of moment diagram that is equals a value of shear. This is still in the positive. We're still in the positive sides. Okay, so we have our V1, V2, and then we have the slope. Okay, the slope that is V1, and then we have another jump in moment equals that is value of a concentrated couple. So we have the external concentrated couple. The difference is we're not going to see any change here on the shear, but in the moment, so this is a constant, but in the moment we are going to see some jump on the on some distance. There's some distance, and then we have a jump. Okay. And then another one. Yeah, change in moment equals area under shear diagram. Okay. Okay, so there are some expressions throughout here. Okay. Okay, I think that's all for today. I think we need more example on the shear and moment. I will try my best to give more practical approach so that we are going to have easier understanding for this concept. Okay. And we still have more example on chapter 4. So this Friday, we go back to chapter 4, have some exercise, the torsions. And next week, I think we go back to here and continue and have more examples on this equilibrium of beams. Okay. Okay. What else do we need? And mostly for some problem solving, I think we can make this problem solving restricted to some simplified geometry like triangles, like distributions, rectangles, triangles. Okay. We are not going to have any like curve that need to take some time to take the integrations. So that will be, I think, I will give you the simplified forms for the problem solving.